Okay, thank you all for coming, and we'll get started. This is the first exam review, obviously, and just so you guys are aware of how this will work, I have these 20 questions that I put on Blackboard that hopefully you've looked at or have with you. They're not real exam questions, but they're pretty darn close, so if you can, it'll give you at least an idea of the distribution of topics that we have, if nothing else. You can interrupt me at any time with questions, whether it's directly related to the problem I'm going over or just something tangential that's still on the same topic, ideally. I don't want you asking me about Lewis structures on the very first question, because that's not till the end, but you get the idea. Just stop me with questions, and any sort of clarification you want on that topic, whether it's directly related to what I'm doing, is fine. And I don't probably need to tell you this either, but if you have to leave early, it's okay. Just get up and go, no problem. Because this will probably be around an hour and a half, but it all depends on how much questions you guys ask, so that's a little bit variable. All right, so with that, we will get right into it and start with question number one. So you will have a question on the exam about early chemical history or mass laws, most likely, the mass laws being the big topic in that first part of the course. So we have this statement here: which mass law is demonstrated by the fact that sodium chloride mined in Goderich, Ontario, which is the largest salt mine in the world, and sodium chloride mined in Kura, Pakistan, at the second largest salt mine in the world, both consist of 39.3% sodium by mass. So for this question, or any type of question where we're given a situation and asked to identify which mass law we're talking about, it's helpful to remember just the real basics of each of these mass laws. So the first three answer choices, A, B, and C, are the three mass laws that we learned: conservation of mass, definite composition, multiple proportions. And so what we want to remember is that conservation of mass is, I think, probably the simplest of the three, in my opinion, is that matter is neither created nor destroyed, specifically in a chemical reaction. So it means that the mass of what you start with and the mass of what you end with are the same. The second choice is law of definite composition. Law of definite composition deals with a single substance, so one substance, a given substance, singular, and that each given substance will have a specific mass ratio of elements. Let's just say has, if I word it this way. A given substance has a specific mass ratio of the elements. So the key distinction between definite composition, which is choice B, and multiple proportions, which is choice C, is that for law of multiple proportions, we're talking about two or more different compounds. Definite composition deals with a single compound and its mass composition, and multiple proportions deals with two or more substances and their mass compositions. Now we're talking for multiple proportions about two or more substances that are formed from the same elements. And there's more to it than that, but at the very basic level, if you're trying to identify whether what we're talking about is the law of multiple proportions, you should look at the problem and say, are we talking about two different compounds, and are we talking about two different compounds that have the same exact elements in them? And then beyond that, there's relationships between those mass ratios that we got into. For this problem, you don't need to think about it in that much detail. So that's A, B, and C. And then choice D here, which is Dalton's law, that's not a mass law. So we're going to eliminate that answer choice, because there is no Dalton's law. There actually is a Dalton's law, but it's not a mass law, so we're going to talk about that later on in the course. Dalton's atomic theory explains the mass law, but that is not considered. Remember, laws and theories are sort of two different things. All right, so in this problem here, are we talking about one compound or more than one compound? One, it's sodium chloride, but it's the same compound in both situations, just from two different sources. They have the same mass ratio. That is clearly going to be then choice B, law of definite composition. All right, a single compound, and no matter where we get that compound from, however we make it, whatever part of the world we mine it from, or whatever the case is, it's always going to have that same mass ratio that's characteristic of that compound. All right, questions on this one or these topics in general? All right, so if not, we'll move on. All right, number two, another question type that you will likely encounter is about subatomic particles. So we dove in right after talking about mass laws into atomic theory and atomic structure. And so if we give you an atomic symbol, whether it be for a neutral atom or an ion, we should be able to figure out how many protons, electrons, and neutrons it has, or some combination of those three things. All right, so we have here the 55 Mn3 plus ion. And so remember that in these atomic symbols, if we have a number to the top left, a superscripted number to the left, that's going to be our mass number, which is A, if you want the abbreviation. But what this tells us is the sum of the protons and neutrons. So there's going to be 55 total protons and neutrons. What we need in this question is neutrons and electrons. So part of that answer is going to come from there, we'll see. And then we have to just go through all three of them. And typically, especially if you want to get, in this case, neutrons and electrons, you also have to figure out how many protons there are first. Because as we said, this mass number is related to the number of protons and neutrons together, so we need the number of protons. And also, as we'll see, the charge is related to the number of protons and electrons, so we need both of those really. So we're going to start with the number of protons. And how do we figure that out from the atomic symbol? What handy guide do we use? Periodic table. Okay, so remember that you're going to have this on the exam, so it's going to be there for you. It's your friend. And you just find that element on the periodic table. Mn was right here. And this whole number above that is the atomic number, which is the number of protons. So there's going to be 25 protons in any isotope, any ion of manganese. Doesn't matter what isotope it is, doesn't matter what charge it has, it will always have 25 protons if it has that atomic symbol Mn. So that gives us the number of protons very easily. Again, that comes straight from the periodic table, the atomic number on the periodic table. And then from there, we just have to use these relationships. So if we want to find the number of neutrons, we know that the protons plus neutrons is equal to 55. That's the mass number, which means the number of neutrons is just equal to 55 minus the number of protons, or 30. All right, so we have 30 neutrons. That's part of our answer. So, and then we also have to distinguish the number of electrons. And then remember, for the number of electrons, if you had a neutral element, a neutral atom, they would have the same number of protons and electrons. In this case, we have a +3 charge, so that means we have 3 fewer electrons, or 3 extra protons, however you choose to think about that. So if we have 25 protons, and we subtract 3 because we have a 3+ charge, so there's 3 fewer electrons than that. That gives us 22 for a number of electrons. All right, so the only answer choice that has both of those correct would be choice B. Okay? Questions on subatomic particles? Yeah. No, the protons is always going to be 25. So protons is dictated by the atomic number on the periodic table, and as long as it's still manganese, as long as we haven't lost any protons from the nucleus, it's going to stay as 25. So whether it's this isotope, a different isotope, whether it's +3, +2, plus whatever, it's going to always have 25 protons. So that number, once you find it in the periodic table, will not change no matter what the charge is. All right, any questions other than that? All right. All right, the next question type deals with photons. So this topic, we introduced sort of the properties of electromagnetic radiation, wavelength and frequency, and then how those are both related to each other and related to the energy of a single photon. Remember, a photon being a little packet of electromagnetic radiation, sort of the electromagnetic radiation analog of the atom, the sort of smallest little piece of that radiation you can have. And we have equations for both of those that we'll cover in this problem. And then the other thing we'll see is that these equations for photons are also going to be relevant for some of the other things we do. Because we talked about, especially in the context of the Bohr model, the ability of atoms to absorb or emit photons related to how the electrons are moving between energy levels. And these photon equations are also important for those types of analyses as well. So in this question, we have an infrared photon with a wavelength of 1234 nanometers. We want to know the energy and frequency. In most problems, you'll just get one of these two, not both, but here I'll do it this way to illustrate both of them in case you come across them. All right, so for the energy part, remember that we have two equations, and the first one is for energy, which is E is equal to h nu. The other relationship that we have is that the product of wavelength times frequency is equal to the speed of light c. So these are the only two equations for electromagnetic radiation that you have to know. That said, it is helpful sometimes because here we have frequency in this energy equation. We're given wavelength. So if we make this substitution that nu is equal to c over lambda, we can plug that in here and write an alternative form of this equation, which is hc over lambda. So these are not two different equations. They're just the same equation where we're substituting lambda for nu related by the speed of light c. So it's same equation really, but just two different ways of writing it, and this one is going to be more convenient in this problem. So for getting the energy of the photon, then we just have to write out the terms. So remember that the numerator here, h and c, these are fundamental constants. Sorry, 626, I always mess that up. 626 times 10 to the 30 minus 34 joule seconds for h, and 3 times 10 to the 8th meters per second for c. Remember that these are on the periodic table, so they're going to be there. Planck's constant is h, speed of light is c. They're both on your periodic table, so you don't have to memorize them. Now here's the part where a lot of people, especially early on, sort of went astray, which is that wavelengths are very often going to be given to us in units other than meters, nanometers being a very common one, especially for visible and infrared light in UV, those sort of regions. And we see that speed of light is in meters per second, so our wavelength will always have to be in meters before we start putting it into this equation and plugging in numbers. So make sure your wavelength is in meters when you're using these equations. Frequency is going to have to be in hertz, which is typically what it will be given to you as if it is given. So we're going to have to first convert wavelength into meters. So we have 1234 nanometers. Remember, there's a table in the review chapter of your book, I think it's R2, I forget the number, that has a bunch of these prefixes for units: micro, nano, milli, kilo, mega, all those. There's a lot of them. There's ones that are sort of boxed in that table that are kind of be the ones that are most common. So especially in this part of the course, you should probably know nano for sure. You should know milli, which is 10 to the minus 3, probably micro, which is 10 to the minus 6. So those three are going to be very common. You probably already know centimeters, which is 10 to the minus 2. And then also the bigger ones, maybe like kilo, mega, giga. So that's like 10 to the 3, 10 to the 6, and 10 to the 9th. So those are the most common ones. And like I said, they will come up, but nano being the one that especially you're likely to see on this test. All right, so we have to convert nanometers to meters. It's 10 to the 9th, or you can put 10 to the minus 9 in the numerator if we prefer. And so what we get is 1.234 times 10 to the minus 6 meters. And so that's the wavelength we're going to use in both of these equations now. So we have a wavelength now that we can put into this equation for energy, 1.234 times 10 to the minus 6 meters. So now meters cancel out. Seconds cancel out, we get an energy in joules, which is what we want. So this is going to be 1.61 times 10 to the minus 19 joules, if I do my math correct. So that's the energy. So only two of the answer choices have that, so we could, if we're confident in that, eliminate the other two. And then for frequency, we just use c over lambda. So we're going to have c is that same constant, 3 times 10 to the 8th. And then we divide that by the wavelength, again in meters, that make sure that the units cancel out properly. And what I got was 2.43 times 10 to the 14th hertz. Okay, so the only answer that has both of those is A. And like I said, it's helpful when you're doing these problems to be at least a little bit aware of typical orders of magnitude. To quickly check yourself. So, if we're dealing with visible, near infrared, or UV radiation, especially that's the type that comes up, especially in those Bohr model questions. The Bohr atom, all those transitions in a hydrogen atom are usually in that relatively narrow region of the spectrum. Your wavelength is going to be on the order of 10 to the minus 6 to 10 to the minus 8 nanometers, let's say. So if it's not in that sort of order of magnitude range, it's probably you can probably mess up the conversion. And similarly, energies of photons for visible, infrared, UV radiation, that part of the spectrum that most of these problems deal with, energies of photons are really small, 10 to the minus 19 in this case, or maybe 10 to the minus 18 or something. So if you calculate a photon energy that has a really large positive exponent, again, check the equation, check your calculator for some mistake. Frequency, similarly, large numbers for frequency, 10 to the 12th, 10 to the 14th, 10 to the 15th, in that range. If you calculate a frequency that's extremely small with a large negative exponent, again, you probably, botch something. So it's always helpful when you're doing problems like this. There's, a lot to check and limited time to do it. But if you can look at an answer and immediately recognize that, oh shoot, that doesn't look right at all, that'll help you check things quicker and identify which ones you need to go over again. So there's a little bit of strategy involved, obviously, with taking any sort of test. And on these ones, for any sort of numerical problem, having at least a ballpark idea of what the answer should be before you start the question can be helpful. All right, questions on this topic or this problem specifically? All right, we will go on then. All right, this one is also sort of related to photons and photon energy and things of that sort, but it's in the context of the photoelectric effect. So if we have the metal hafnium, we observe that light with wavelength less than 318 nanometers is required to eject an electron from the surface via the photoelectric effect. So we want to know what is the threshold energy, sometimes called the work function, for this metal in joules. So this is worded in a lot more complicated way, but essentially it's the same type of question. So remember, at the photoelectric effect, we have a metal surface. And we shine light on that surface. And that light is going to have some characteristic frequency, nu. And the energy of that photon is going to be equal to h times nu. And if that energy, the product of h and nu, is greater than E0, which is our threshold energy or work function, we will get electrons ejected from the surface. And depending on what the exact energy of the photon is, as long as it's bigger than the threshold energy, it will eject electrons, and how big that photon energy is will determine what the kinetic energy is of the ejected electron in excess of that threshold energy. All right, so again, we're not going to really do calculations of kinetic energy for ejected electrons in this test, but you should know the concept of photoelectric effect and the idea that we're shining photons onto a surface, ejecting electrons, and those photons have to be greater than the threshold energy for anything to happen at all. So here we're telling you that the wavelength that's required is 318 nanometers, and we want to know then what is the energy then that corresponds to, what is the energy of that photon. So all we're really doing is just relating the threshold energy to that wavelength. So the threshold energy or work function, those are two terms for the same thing, is given by, again, E0, that minimum amount of energy needed to eject an electron, and that, by those same exact photon equations, is related to the minimum frequency and the maximum wavelength. So it's h times the threshold frequency nu, which is equal to hc over the threshold wavelength lambda. Now remember, because energy and wavelength are inversely related, if the energy needs to be larger than E0, that means the wavelength needs to be smaller than lambda 0. So that's what this problem is telling us. So 318 nanometers is exactly the right amount of energy to eject an electron. If you want to have more energy than that, the wavelength needs to be smaller than that because there's that inverse relationship. But the whole point of this is we just need to plug lambda 0 into this equation to find out what the threshold energy E0 is. All right, so the threshold energy is just going to be hc over lambda. All right, so this is exactly the same type of computation as before, just disguised a little bit differently. So we use the same constants. All right, and again, we have to convert wavelength into meters, so it's 318 nanometers. We divide that by 10 to the 9th, and we get 3.18 times 10 to the minus 7 meters. All right, so I'm not going to review that step again, but we have to convert into meters. And so then our answer comes out to 6.25 times 10 to the minus 19 joules. All right, so that would be choice D. And remember, as I said in the last problem, photon energies tend to be small, so that could allow us to eliminate choice A without even looking at it. Even choice B, it is a negative exponent, so maybe it's not obvious that that's too large, but that's still, several orders of magnitude larger than a typical photon energy for something in the, 300 to 800 nanometer range that we usually work with in these types of problems. So again, helping these little order of magnitude things can be helpful, though not necessary to solve these problems. All right, so questions on this one. Again, the equation's the same, but anything on the concept of photoelectric effect, which, there are a couple questions that could pop up on that for you guys. All right, quite a bunch today. Let's go on then. All right, so here we want to know the frequency of a photon needed to promote an electron from hydrogen's ground state into the third shell. So this is the other very common context that these photon relationships come up in, is in the Bohr model and moving electrons around in the hydrogen atom. So we're going from the ground state to the third shell, and we want to figure out what the frequency of that photon is. Remember that if we're going from a lower energy level, a smaller value of n, to a higher energy level, which is a larger value of n, we require a photon to be absorbed, and the energy gap between those two values of n is equal to the energy of the photon that's absorbed. So these types of problems typically are going to have two steps involved. You're going to calculate that energy gap between the two levels that we're talking about here, and then you're going to relate that to the photon, either its wavelength or frequency very often. Sometimes we'll just ask for the energy of the photon or the energy gap itself, and then you just have to do the first step. But in this case, there's going to be two steps. So the first thing we think about whenever we see hydrogen atoms, ground state, third shell, all these key words for us, we should immediately zoom in on that Bohr equation, delta E, which again is the energy difference between two levels defined by their quantum numbers n. This one, I don't think this constant was on your periodic table, so you have to remember it. And then for hydrogen, we just have the n values. Again, there's that z squared term, which is the number of protons, but all the calculations we'll ask you to do are for hydrogen, so you can just leave that z term out because it's 1. And so again, that's the delta E. That's the difference in energy between these two. So remember that ground state tells us that we're starting with n equals 1. And then we're going to the third shell, which means that the final value of n is 3. Okay? So ground state always means n equals 1. And then we have to just put those two in for this equation. So minus 2.18, 10 to the minus 18 joules. The final value of n, if we want the sign of this to be correct, we need to put these in the right order. So it's 3 squared, that's the final value of n, 1 squared, which is the initial value. And so what we get is a delta E of 1.94 times 10 to the minus 18 joules, meaning that when the electron absorbs this photon, it gains 1.94 times 10 to the minus 18 joules of energy, or another way to think about that is the gap between those two energy levels, n equals 1 and n equals 3, is exactly that number, 1.94 times 10 to the minus 18 joules. Now once we have that number, what we're looking for is the frequency of the photon. And remember then, anytime you have a process like this in a Bohr atom, absorption of a photon or emission where you're moving in the opposite direction from higher n to lower n, the energy of the photon is just given by the absolute value of that delta E. So whatever energy gap that electron is moving between is going to be equal in magnitude to the energy of the photon. Again, photon energies are always positive. You can't have a negative photon energy, but the magnitude is always just given by delta E. And that's going to be equal to h times frequency, which, as we said, is hc over lambda. So same equations now will come into play to figuring out what is the frequency or wavelength of this photon. Here we're looking for frequency, so the frequency is just going to be the energy of the photon divided by h. And that's going to be, the energy of the photon is this. Where did my highlighter go? You guys are probably like mad now because I don't have my highlighter. What is that program called? I have to open it back up because I had to restart my computer. Pointer focus. Instead of this little blue dot that doesn't register very well. Okay, so we're back and we have a pointer now. And what I was trying to point to when I realized I didn't have my pointer is this number here. That's the energy of our photon, which is, as I said, equal to the energy difference between the two energy levels. So we're going to put that in to our equation, and we're going to divide by that same Planck's constant h. And what we get is 2.928 times 10 to the 15th hertz. All right, now remember when we have these large exponential answers, and if it's a numerical type of problem where you have to type your answer in, not a multiple choice, there are now two ways that we would have you enter the answer into Blackboard. So you have to read the directions of the question. The reason there's two different ways is because the old version of Blackboard could not handle exponents very well. The new version is no problem. So we have two different possibilities here, depending on when the question was originally written. All right, so you could either write it as 2.928 capital letter E15. So that's one way to enter the answer into Blackboard if we ask for the answer in exponential form. The other thing that's from the older versions of the question is to take the log of that, which is what I asked you to do here. So the log of that number, learn how to do that in your calculator because it's not easy to do in your head. Typically, if you have like a TI scientific calculator, which a lot of you do, you just have the number on your calculator, you press the log key, and that gives you the number. Syntax could be different for other calculators, so make sure you're familiar. And what we get for this is 15.47. I think I said 2 decimal places, so that's sufficient. And we just report it like that. Again, if it's a number with a 10 to the 15th exponent, the log should be 15 point something. So make sure your answer is reasonable and that they line up with each other. All right, questions on this? Yeah. The ground level is not at the nucleus, but it's the orbit that's closest to the nucleus. That's n equals 1. So n equals 1 is the ground state, and that's the orbit that's closest to the nucleus. The nucleus doesn't have an n value associated with it. N values are only for electrons, which in the Bohr model are orbiting around the nucleus in regular circular patterns. Well, so the ground state for hydrogen and helium would have all the electrons with n equals 1. Beyond that, you have to start filling n equals 2 to accommodate those electrons. But the Bohr model, which we're dealing with here, only deals with hydrogen, and the ground state is n equals 1. Yeah. No. For sig figs, just follow the directions in Blackboard. I suppose if we don't specify, you should make sure you enter at least enough sig figs. Don't round your answers too much. But it's not going to count it wrong if it's the wrong number of sig figs. And usually we'll tell you enter it to 2 decimal places or 3 or whatever, just to make sure that your answer is precise enough for that to not be an issue. Okay, questions otherwise? Okay. All right, now we're on to quantum numbers. We want to know which of the following set of quantum numbers is valid for a 4D orbital. All right, so remember, if we give you a number and a letter, 4D, that's going to tell you really 2 of the quantum numbers right off the bat. So 4D, the number is the n value. So remember we have quantum numbers n, l, m sub l, m sub s. So those are the 4 quantum numbers. Here we're only looking for 3 of them because it's just the quantum numbers for an orbital, not for an individual electron. And the letter here relates to the value of L. The most common being 0, 1, 2, 3. So remember that L can start at 0 and goes up to a maximum of n minus 1. And that's going to be S, P, D, F. Beyond that, we don't see these as often because they don't occur in the ground states of real atoms. But we'd have 4, 5, 6 would be, they go alphabetical after that. So G, H, I. I think we skip L, but you wouldn't go really beyond that anyway, I don't think. So I think 7 would be technically K. But we're not going to be really responsible for that. But if you were wondering what happens beyond L equals 3, you go alphabetical pretty much. I'm pretty sure you skip L because L is the quantum number, so it's confusing. All right, but all we care about here is L equals 2 because that's what D corresponds to. So that means L equals 2. So the only answer choices we could even begin to pick are ones that have n equals 4, L equals 2. That'd be the first 2 numbers. So A is okay, B is okay, but C has the wrong L value. And E has the wrong L value. Here L equals 3, it should be 2. Here L equals 1, it should be 2. So we get rid of those 2 answer choices on the basis of the second quantum number L. And then from there we need to figure out which is the allowed values for m sub L. So we have to recall that m sub L goes from minus L to plus L, including 0. And so if we have L equals 2, we start with minus 2 for m sub L, and we go minus 1, 0, 1, and 2. So our m sub L value has to be one of these numbers to be a 4D orbital. It can't be anything beyond these. And so if we look at choice B here, it has invalid m sub L number. M sub L cannot be 3 if L is only equal to 2, and we cannot have half integer m sub L values. All the m sub L values are positive or negative, but all integers. So the only one that works is choice A, -2 being the smallest value of m sub L, but still one that is valid for a 4D orbital. Okay, any questions on quantum numbers? All right, so this is a typical type of question, just knowing the rules for quantum numbers, knowing how to identify subshells and orbitals based on quantum numbers. So review that, yes. How do we get m sub L? Well, m sub L can be any of these 5. So we're just looking for a valid set, which means m sub L could be any of these 5 numbers, -2, -1, 0, 1, or 2. So if there were 2 answer choices that had those, then those would both be correct. But we only have one here that works. There's no answer choice that allows you to pick more than one here. So, all right, anything else? All right. Another question about quantum numbers, and we want to know how many orbitals are in the sublevel where n equals 5 and L equals 4. Now, there's a long way and a short way to do these types of problems. So if we give you values of n and L, or one or the other in some cases, we will sometimes ask you questions, these next two really deal with this, about how many orbitals, how many electrons, and so on. The long way to do it is remember that an orbital is a set of 3 quantum numbers, n, L, and m sub L. So you could figure out for this value of n and this value of L how many different m sub L values there are, and each of those individual m sub L values corresponds to one single orbital. But there are some shortcut relationships that are helpful to remember. So if we tell you the shell number n, so in a given shell, which remember that shell is defined by a value of n, the first quantum number, if you want to know the number of orbitals, it's just given by n squared. And then for a subshell, remember a subshell is an n and L together, or sometimes just an L by itself, you would say for this type of subshell, for an L equals 2 subshell, which could have different values of n. But if you're given the value of n and L, or just the value of L as a subshell designation, the number of orbitals is given by 2L plus 1. Now that comes from the relationship we talked about in the last problem, which is that the allowed m sub L values are -L to plus L, including 0, so that's where you get those 2L plus 1 allowed values. In this problem, we're given n and L together, so we're going to use this relationship to figure out how many orbitals are in that subshell defined by those 2 quantum numbers. So L is equal to 4, but then you have to use the letter designation to find that. And so there's going to be 9 possible orbitals. Again, each of those orbitals has a unique m sub L value, which would be, if we want to write them all out, -4, -3, -2, -1, 0, 1, 2, 3, and 4. So those are the m sub L values, 9 of them. That's why we have 9 orbitals. But if you remember the 2L plus 1 relationship, you don't have to write out all these m sub L values. So there will be 9 orbitals in the n equals 5, L equals 4 subshell. Now another relationship that comes out of this, which we'll actually use in the next problem, but I'll give it to you here because it follows directly from this, is we will sometimes ask what is the maximum number of electrons that can go into a given shell or subshell. And for that, we have to recall that an orbital, a single orbital, can hold how many electrons in total? 5 electrons in one orbital? Yes, 2. Okay. So there's 2 electrons maximum per orbital, spin up and spin down. And so if there's a maximum of 2 electrons per orbital, we just double these relationships to figure out how many electrons would be allowed to be in one of those shells or subshells. So for a given shell, the number of electrons, again, this is maximum. This is not how many they will always have, but the maximum number of electrons is just given by 2n squared. We take the number of orbitals and just double it. That's going to be, again, maximum, not necessarily how many it will have. And for a subshell, we have 2 times 2L plus 1. That being the maximum number of electrons that can go into a subshell. So those relationships are very closely related to each other, and both of them could come up on this part of the test. All right, questions? Yep. Because we're giving here a sublevel defined by n equals 5 and L equals 4. So if we use the n squared equation, that would give us 25, but only a portion of those orbitals are going to have L equals 4. The rest of those orbitals would have either L equals 0, L equals 1, L equals 2, L equals 3. We would just want the ones that have n equals 5 and L equals 4, so we have to use the L value to determine that. Okay. If we use the n value, we'll get a number too large, because that would give us all of the n equals 5 orbitals, not the ones that have L equals 4 necessarily. Anything else? Yeah, level or shell. Shell is more common, but subshell, sublevel are kind of both used. But yeah, the word sub would tell you whether it's L or N that you should consider. Okay? Anything else? All right, next question is very similar. We have, what is the maximum number of electrons allowed in the n equals 5 shell, and how many of these can reside in the 5f subshell? So two-part answer, and we're going to use those exact same relationships we talked about for number of electrons, where, again, it's helpful to remember these relationships because especially for larger values of n and L, having to sort of write out all of the possible combinations of quantum numbers takes a long time. So these are definite shortcuts for you to allow you to save some time on these types of questions. So here we're just, we want to know, first, how many total maximum number of electrons in the n equals 5 shell. So for that, we're going to use the n value because we want to know the total number of electrons that goes into that entire shell. So if n equals 5, the maximum number of electrons, as we said, is given by 2n squared. There's n squared orbitals, a possibility of 2 electrons per orbital, so we just take that relationship, 2 times 5 squared. So in the n equals 5 shell, there can be a maximum of 50 electrons. Okay? But if we want to look at 5f, now we want to know how many of these 50 electrons reside in the 5f subshell. So that should be some number less than 50, obviously. We want to look at, for 5f, in this case we have a value of n and a value of L, so we're going to use the equation that involves L to figure out how many total electrons could be in this subshell. So the number of electrons in a subshell, as we said, with an n and an L value considered, is 2 times 2L plus 1. And we have to figure out again the value of L because we're given a letter F. L is 0, 1, 2, 3, and so on, and that's going to be S, P, D, F. So we want to use L equals 3 for this one because it's an F subshell. All right, so there's 14 in the 5F subshell maximum. So the correct answer would be choice C, which is 50 electrons for n equals 5, 14 of those being in the 5F. Now, any F subshell would have 14 electrons. Remember, it doesn't matter what the value of n is for these subshell relationships. So 4F, which is the first F subshell, could also hold 14 electrons. 5F holds 14, 6F holds 14, and so on. That you could also figure out from the periodic table because F subshells do show up on the periodic table. There are these ones down here, and if we see how many columns there are in these 4F and 5F, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14 elements, meaning that you can put up to 14 electrons into the F subshell. So that relationship is helpful, like I said, the 2L plus 1 doubled relationship here, but you could also, for this one, have consulted the periodic table to help you out. Any questions? All right, same topic, but any last questions before we go to the next ones? Okay. All right, so now that we've talked about subshells and quantum numbers and those things, there are going to be at least one, possibly more than one question that deal with electron configurations. We have 2 in this review, and that's probably a typical number you'll see on the test. Keep in mind the way we do these tests, if you're not familiar with the inner workings of Blackboard. So there's 20 questions for you guys. That's going to be every single midterm is 20 questions. For each of those questions, Blackboard has a bank of, let's say, 15 to 30 questions that it draws from. So there's, 600 or so total exam questions probably. And I did go through all of them to make sure they were accurate. Hopefully there's no mistakes or anything. And so so you're not likely to get the same questions as your neighbor. You're not likely to get the same questions that you have in the practice test, but there's going to, potentially be some of you that have the same ones. That also keep in mind that they're arranged by topic. So they're not randomly, each question is not randomly drawn from the full 600. It's randomly drawn from a subset of those which are arranged by topic. So question 1 will be a question about mass laws or early chemical history and so on. Question 2 will be a question about, I don't remember what it's about, but some certain topic of the course, and so on. So you're not going to get the same topic 20 times. They're going to be distributed amongst the different topics for everybody, but slightly different questions, of course. All right, so here we have electron configurations. So you will almost certainly get a question about electron configurations, or possibly 2. And we want to know the electron configuration for manganese. Now, we saw manganese earlier in this. This was the one that has the atomic symbol Mn. And this is one of the ones you are expected to know. So there are going to be a few questions on there. We're not going to specifically, in many cases, test you about atomic symbols and names, but you do need to know the first 36. Not what order they come in, but which symbol goes with which name. So in this problem, if we ask about manganese, you need to find it on the periodic table by its symbol, because as you recall, our periodic table does not have the full names on it. So we need to know that manganese Mn is the symbol, so that's what we're going to zoom in on. And then we have to determine the correct electron configuration for this. Now when you're doing electron configurations, whether we ask you to produce the configuration, most of those being multiple choice questions, or we give you the configuration and ask you to identify the element, I think the first thing to look at is how many total electrons there are. Because if the configuration does not have the correct number of electrons in it, it can't be the right one for that element, regardless of what the subshell designations are. So if we have Mn, which as we said before is atomic number 25, as a neutral element, as a neutral atom, it should have 25 electrons. We also see that the noble gas that comes before it is argon, so all of these configurations that I gave you start with argon. Now that total number of electrons is actually not going to help us here, because all of these, remember, argon has 18, all of these have 7 more electrons beyond that, so all of these have the correct number of electrons. So we can't use that shortcut to eliminate any answer choices here. Sometimes you will, sometimes you won't, but these all have 25 electrons in them, so they all could be correct. We have to figure out which one it is. So if we go back to the periodic table, argon is the previous noble gas. That's how we're going to abbreviate those 18 core electrons. And then we go in numerical order. So we come down here to this part of the periodic table, which is right after argon. This is the 4th row, so this is going to be the 4s subshell. We fill it up with 2 electrons to get to atomic number 20. And then to get to manganese, remember after 4s, this is the D block, but it's the n-1d. So it's not 4d, it's 3d for this first row of the D block. So it's going to be 3d, 1, 2, 3, 4, 5. So 3d5 takes us to manganese, so we have that many d electrons, 3d electrons, in the configuration. So when we write that out, what we get is, again, an argon core. We said we go through the 4s block to fill that with 2 electrons, and then 5 3d electrons gets us to manganese. All right, so the only one of those that works is choice A. In this one, we have 4p5, which would have skipped the 3d altogether. Remember, we can't skip any numbers on the periodic table. We have to go through all those blocks in order. We never skip around. This one, remember that it's going to be n-1d. So after 4s, it's not 4d, it's 3d. So that's why choice C is wrong. It should be 3d5, not 4d5. And then remember, here we're in the 4th period. So the principal quantum number is 4, and that means the S block should be 4s2. So, these are all similar to each other, but the only one that has the correct subshell designations is choice A. All right, questions on this one? Yes? Yeah, yeah. I think it's a piece of paper. So it's like there's like a little cubicle, I guess, that you're sitting in, is taped to the wall. So I try to avoid Casa, just like you guys, but I haven't been there in a while. So that's how they do it. All right, any other questions? Yeah. Yeah, so for the D block, the question was, every time you look at the D block, we should subtract 1, and that's essentially correct. So the first D block occurs in the 4th row, but it's 3D. The 5th row D block is actually 4D, and this is 5D. So these are all n-1D. These are n-2F. So this comes from the 6th row of the periodic table, but it's actually the 4F, and this would be the 5F coming from the last 7th row of the periodic table. So you have to remember that, yeah, those orderings are a little bit different. They're not purely numerical in that case, but they do fall right from the locations of the elements on the periodic table. All right, the last thing I should point out about this is, again, there's a couple of exceptions to electron configurations. We only want you to know 2 of them. There's more than that, but there's only 2 that we expect you to know. So remember that chromium, it's the one right next to manganese. We would predict that it's 4s2 3d4, but in reality it's 4s1 3d5. So this one violates the Aufbau principle because we take 1 electron from the lower energy 4s and put it up to the 3d. So again, we would predict s2d4, but we move 1 electrons up. And then copper, we would predict a 4s2 3d8, but we actually get, sorry, that's not the right number of electrons. We would predict 4s2 3d9, but we get 4s1 3d10. So 2 exceptions where we violate the Aufbau principle, take an electron from a lower energy subshell and move it up. And the reasons why we do that are a little bit beyond this course. You'll talk about that if you ever take physical chemistry in the future. Okay, any questions on electron configurations? All right. And this one is also related to that. We want to know which of these orbital diagrams reflects an atom in the ground state. So there are 3 rules we have to follow when we're filling electron configurations, and one of those rules you can get from just the configuration itself, that being the Aufbau principle, which is the one that says you should fill the subshells from lowest energy to highest energy. So we should think about the Aufbau principle, which is lowest to highest energy subshell. So we fill them in that correct order. And that is borne out directly in the configuration, the one that we just did in the last problem. You can tell whether or not we're following Aufbau principle by whether we fill those subshells in the correct order. The other 2, though, you have to look at these more detailed diagrams that show the individual orbitals that the electrons come into as well as their spins in most cases. So the other one is Hund's rule. Which is that we want to maximize the number of unpaired electrons. All right, so Hund's rule says we want the maximum number of unpaired electrons, meaning that it especially applies for degenerate subshells. If we have more than 1 orbital to fill that are at the same energy, we fill them one at a time, all with the same spin. And then finally, we have Pauli exclusion principle, which says that no 2 electrons have the same quantum numbers. So every electron in the element will have, in the atom will have a unique set of quantum numbers. Now, how does Pauli exclusion manifest itself? So Pauli exclusion says that you can't put more than 2 electrons into a single orbital. So in these types of diagrams, each box represents an orbital. And so you can't put more than 2 in a single box, so that violates Pauli exclusion. Also, if you have 2, they have to be 1 up and 1 down. So any other combination of more than 2 electrons, or if you had 2 with the same spin in the same box, that would violate Pauli exclusion. I don't think we'll see that in this problem. But then evaluating these answer choices, let's see which of these do follow those rules. So in this configuration here, we fill the 1s and the 2s before the 2p, so the Aufbau principle, we're fine. But then if we look at this arrangement here, we have 1 spin up and 1 spin down. Remember, our goal is to maximize unpaired electrons, so if we put the first electron spin up, the second one should also be spin up. So this one is going to violate Hund's rule, so that's not going to be our ground state configuration. In the second configuration here, we have a filled 2s, but we have a filled 1s, a partially filled 2s, and then we already started putting electrons into 2p. So we're filling these in the wrong order because we would need to fill up the 2s before adding any electrons to 2p. So again, this empty spot here tells us that we're violating the Aufbau principle, that we're skipping a subshell and going to a higher energy one before that one is filled. So the Aufbau principle says we will always completely fill a subshell before moving on to the next one in energy. Again, those 2 exceptions I gave you on the last one violate that, but those are the only 2 exceptions that you guys will be responsible for. This one here, we fill the 1s, we fill the 2s, and then our 2p has 2 electrons, both spin up, both in separate orbitals. So this one looks like it's going to be okay for us. Now some people get confused because they say, well, shouldn't they be in the first 2 orbitals? Remember, the order we fill them in is arbitrary. So you can have these 2 electrons can be in any combination of 2 orbitals as long as they're 2 different orbitals and they both are spin up. So they could have been both spin up, or they could have both be spin down too. It doesn't really matter that way either. So as long as they have the same spin and they're in two different orbitals, that's all that matters. So there's a lot of combinations that would work for that. I think there's at least probably 6 combinations that could represent that ground state. So you could have them, like we show here, you could have them both spin up in the first two, both spin up in the last two, or both spin down in any combination of two orbitals, as long as they're the same spin in two separate orbitals. So that one works out. It's not written in the most conventional way. And then finally, choice D here, we have another violation of Hund's rule, because these are all P2. This is another P2 configuration, which again would have the 2 electrons in separate orbitals with the same spin, not paired up like this one. So choice C is the only one that follows all 3 of these. None of these violate the Pauli exclusion principle, but a couple of them violate Hund's rule, and one of them violates Aufbau principle. So the only one that's a ground state, which follows all of those, is choice C. All right, questions? All right, let's just plug forward then. Halfway there. All right, so now we're talking about classifications of elements on the periodic table, which once we have the electron configuration, we can predict certain properties of them. So we're looking for the correct classification and the expected monoatomic ion charge. So in other words, what kind of element is this? And when it forms an ion, what's the charge of that ion? And we're going to see which of these all have that information correct. All right, so the first one is potassium. So we have to know the symbol for potassium. Anybody want to hazard a guess? K, it's a weird one, but it's K. So we need to find K on the periodic table and figure out which type of element it is and what's its expected charge if it forms an ion. So K on the periodic table is number 19, which is here. And what we can see is that it's on the left side of the periodic table, so it's a metal. And all of the metals that are in these first 2 columns, or the few that are in the P block over here, those are all classified as main group metals. So anything in the S block and the P block is called main group. Any of the ones that are to the left of that staircase will be classified as main group metals. So that's the correct classification for potassium, K. It is a main group metal. But then what charge would we expect it to have if it forms an ion? +1, because it's in the first column, it can lose 1 electron and get to a noble gas configuration. So the charge here is wrong. That should be +1. So this one is not correct. We're looking for the ones that give the correct information. All right, and then we have aluminum. Symbol for aluminum, anybody? Al, so that's number 13. So this is this also a metal or not? It's not the most obvious, but it is. That staircase starts at boron and kind of snakes down like that. Aluminum does border to the staircase, but it's a metal and not a metalloid. So it's helpful to remember that. I think we can be comfortable with the fact that aluminum is a metal, because if you've seen aluminum foil, it certainly looks like a metal to me. So hopefully that doesn't ruffle any feathers. And the other part about aluminum that's not obvious, and one of the reasons that I put it in this review for you to be able to see it, is what would be the expected charge for aluminum. It's not the most obvious either. So I heard a +3, which I agree with, because the configuration for aluminum is, the valence configuration is 3s2, 3p1. It has 3 valence electrons, and it is possible for it to lose all 3 of those to achieve the neon configuration. So +3 is the only charge that aluminum forms, at least commonly speaking, in stable ionic compounds. So this one is correct, because it is a main group metal, and it does form +3 cations. And finally, selenium, symbol, Se, that's number 34. This is to the right of the staircase, so what does that make it? Non-metal. So we have metals and non-metals are sort of the grossest classifications. There's some distinction within there, so it's a non-metal, and then what charge would it form as an ion? It could be +6, but remember, we don't go that high. So anything on the right side of the periodic table forms anions. They gain electrons to get to the nearest noble gas. So selenium can gain 2 electrons and get to the krypton configuration, so it will be forming a 2- anion. All right, so this is all correct also. I'll write the symbols here so people have them. And so choice E, both 2 and 3, are all correct for that type of information. All right, questions on classifications or ion charges? All right, on to the next one. All right, we also have Chapter 2 was a very dense chapter, as we saw. And another thing we covered were periodic trends. So our ability to use the electron configuration and the location on the periodic table to predict radius, ionization energy, electron affinity, electronegativity, those being the big ones. Now, when we're thinking about this, though, we have to remember that periodic trends really only exclusively work for neutral elements, for neutral atoms. If you're starting to talk about ions, you know, what's the ionization energy of this ion, or what's the radius of this ion, the periodic trends are not necessarily going to be what you look for. In some cases, they're still relevant, but there's other things we want to think about first, and the first things we want to think about are, there's a few relationships that we'll cover in this problem. So here we're looking for which one has the largest radius, and we have a combination of elements and ions, so we're going to have to really use a few different relationships for atomic radius and ionic radius to get this. So like I said, the easiest thing to do in these types of questions where you're ranking or finding the biggest or finding the smallest is do two at a time. It's hard to think about more than two things at once, so let's do two at a time and compare the ones that are very straightforward comparisons. As we'll see in this problem, sometimes you'll try to compare two and you're like, I don't really know. But as long as there's an unambiguous winner, that comes out of that, however many comparisons you need to do to get to that, you'll still be able to get the answer. So if you're not sure about a comparison, skip it and try to do a different pair of them and compare those two. So we'll see how that works here. All right, so we can pick any two. I think the easiest ones to start with are comparing the neutral elements to the anions. Okay, so if we have oxygen to oxygen 2 minus, so what happens when we add electrons? Does it get bigger or smaller? Bigger. All right. My passive-aggressive response convinced people to change their answer. That's what I wanted. All right. So if we have anions, we're adding electrons, and that's going to make them bigger. Now, typically when we form anions, we are adding electrons to the same subshell, so that subshell is not necessarily farther away from the nucleus. But remember, what we're doing is we're forcing extra electrons in there. Electrons are going to start repelling each other, so they're going to want to spread farther apart to reduce that repulsion. So anytime you add extra electrons to something and form an anion, its radius will get bigger. And it's actually a pretty big effect. So we're not going to hold you responsible for the exact numbers, but anions are much larger than neutral atoms. I'm trying to remember one off the top of my head, but I think chlorine, so we're going to do that comparison here. So in terms of radius, O2 minus should be way bigger than oxygen. We're adding 2 extra electrons, its radius is going to swell up quite a bit. Same story, so if we're looking for the largest one, we can now get rid of oxygen because oxygen is already smaller than O2 minus, so it can't be the biggest of all 4 of these. And then similarly, if we do Cl versus Cl minus, Cl minus is an anion, it has 1 extra electron. That will cause the radius to get bigger. So this is also going to be bigger than its neutral atom Cl. So we can eliminate the neutral Cl as being the biggest. All right? So those are the two that are left, the two anions. And sort of illustrate how big an effect this is, if I remember this correctly, I don't know if these are the exact right numbers, but chlorine has an atomic radius of 73 picometers. And then the anion Cl minus has a radius of, over 100, so almost twice as much. So it's a really big effect just by adding 1 electron. All right? And then finally, the last comparison is O2 minus versus Cl minus. Now, when we're comparing two anions, they are different charges, so that maybe complicates the picture a little bit. But the first thing you want to think about is what subshells are those electrons in. Okay? If they have the same number of electrons in the same subshells, the one with more negative charge is going to be larger. But if they have different subshells, we need to also consider how far away is each of those subshells from the nucleus. So in the O2 minus anion, where do those valence electrons end up? Which subshell is this? It's the second row, and it's which block of the periodic table? So it says 2p. So the O2 minus valence electrons are in the 2p subshell, but Cl minus is which subshell then? 3p, because there's one row lower on the periodic table. So this has 2p valence electrons. This has 3p valence electrons. And remember that the value of n dictates how far the subshell is from the nucleus. That's also a very large effect going from n equals 2 to n equals 3. So we would predict then that this is going to be the largest because 3p is further from the nucleus than 2p. So once we start comparing two anions, we can't just use periodic trends anymore necessarily because, again, they have different numbers of electrons. They're no longer neutral atoms. So we have to think about what subshells the electrons are in. So this one's 3p, so that makes it the largest one. So this gave you sort of a combination of the types of comparisons you're going to do. Neutral atoms to ions. Here we compared to anions, which got larger. Cations would get smaller than the respective atom, and so on. All right, questions on this one or the trends for radius? Okay. All right, in this question we're talking about ionization energy. For the element phosphorus, which ionization energy will show an exceptionally large increase over the previous ionization energy? So remember that we have periodic trends for ionization energy, but that only deals with the first ionization energy, the removal of the first electron. But for any element that has multiple electrons, we have successive ionization energies that refer to the removal of additional electrons one at a time. So we have, for phosphorus, there's a lot of electrons. We have a lot of ionization energies, and we want to know which one of these ionization energies will show a very large spike. In other words, it will increase a lot relative to the one that comes before it. All right, so the first thing we have to think about is the electron configuration, or more specifically, the number of valence electrons. So for phosphorus, the electron configuration is going to be, we have neon, so phosphorus is here, number 15. Neon is the noble gas that comes before. We go to 3s2, 3p, 1, 2, 3. So we should be able to get that configuration. But all we really care about for ionization energies and where we're going to see that large increase in ionization energies is how many valence electrons there are. So we have to think about how many valence, and that's going to be 5. Because remember that for p block elements, the s and the p outer electrons are all valence. There's 5 valence electrons here. The other way we can get that information for the main group elements is the group number. So phosphorus is group 5a, Roman numeral 5 on our periodic table. So that means it has 5 valence electrons. So that's another shortcut you can use. Now the reason this is important for this question is because removing valence electrons is relatively easy. They get harder and harder. Each time you remove one, it does become harder to remove another one, but they're relatively easy to remove valence electrons. So for the first 5 ionization energies, we're still removing valence electrons. So all 5 of these involve removing valence electrons, which is relatively easy. Now they do increase each time. They don't get smaller. They do increase each time, but they're still increasing gradually. It's a pretty gradual increase as we each remove valence electrons. But then once we get to the 6th ionization energy or beyond, we start removing core electrons. And these are very difficult to remove because they're closer to the nucleus, they're held on much more tightly, and so it's really difficult to remove those guys. So we'd have a huge jump here. So there's a big jump from 5 to 6, and then these will continue to increase as we remove more and more core electrons. So the big jump occurs between valence and core electrons. There are 5 valence electrons, so the first 5 ionizations involve removing those valence electrons. It's the 6th one where we have to start pulling off core electrons. So the correct answer then for this was D, because that's the one that's going to involve a large increase over the previous one. All right, questions on that concept or ionization energies in general? All right, we're into now, for keeping track of our progress, we're now into chapter 3 topics, which is dealing with bonding and formation of compounds. And for this, we want to determine the least polar bond among the following. So if we're looking, so remember that polar can also be written as, or polarity, I guess, percent ionic character. So just make sure we're familiar with the terminology. This one's asking for least polar. We could have asked for which one has the smallest ionic character or smallest percent ionic character. Those kind of mean the same things. Remember that polarity is unequal sharing of electrons. In the extreme of a polar bond, the electron completely gets transferred from one atom to the other, and you have an ionic bond. So ionic character is how polar that bond is another way of saying that. So here we're looking for the least polar, and remember that we're looking for difference in electronegativity. that's going to dictate how polar the bond is. So the larger the difference in electronegativity, the more polar the bond is. So we're looking here for the one that has the smallest difference. And as with most of these problems, comparisons of two at a time can be helpful. And so what we're going to do, and especially ones that have one of the elements in common, okay? So if we're looking for the least polar here. If we have carbon, oxygen, and carbon, chlorine, they both have carbon in it. And so we have to figure out which of these does carbon have a greater difference in electronegativity, which one is the larger gap between those electronegativities of the two elements. So we go to the periodic table. Electronegativity increases as we go up and to the right. Oxygen is the second most electronegative element on the periodic table. So the carbon-oxygen bond is going to be polar. Oxygen is more electronegative than carbon. Sorry, oxygen is more electronegative than carbon. And so you're going to have a partial negative charge on oxygen. Chlorine is down and to the left, down and to the right, so it kind of has two opposing trends. Remember, electronegativity increases left to right, but it decreases top to bottom. So is this an increase or a decrease? This is where it's helpful to remember that oxygen is the second most electronegative element. So it's more electronegative than chlorine. It's not obvious from their location, so it's helpful to remember at least a few of them to orient yourself. So between carbon, oxygen, and carbon, chlorine, both of these are polar, delta plus, delta minus. We would expect carbon, oxygen to be more polar because, again, oxygen is the second most electronegative atom behind fluorine, so it's going to be the most polar carbon bond with carbon over any other things besides fluorine. So that's the more polar one. We're looking for least polar, so we can eliminate this one because we're looking for least polar. So now we have to compare carbon chlorine to carbon fluorine. This is actually an even easier comparison. Okay? Because chlorine is here, fluorine is here. Both of them are more electronegative than carbon, but fluorine is the most electronegative atom, so when it's bonded to carbon, it's going to have the most polar bond. All right? Because this is the least electronegative pair, so it's the difference between those two. The difference between carbon and fluorine is larger than the difference between carbon and chlorine. So that's a more polar bond, carbon-fluorine bond. So in terms of polarity, they would rank that way, so we can eliminate this one. Again, we're looking for the least polar here, so whichever one is the more polar in these comparisons, we can get rid of. And then the last comparison here is carbon chlorine versus silicon chlorine. Now the common element they have in common is Cl, chlorine. In both cases, that's the more electronegative of the two, so we have to figure out which between carbon and silicon, which is least electronegative, which would give us then the greatest difference in the electronegativity. All right, so chlorine is here. So we have carbon versus silicon. Remember that electronegativity decreases as we go down. So silicon is less electronegative than carbon. So the difference between silicon and chlorine is larger than the difference between carbon and chlorine. So that would be a more polar bond. All right. And so the one that ends up being the least polar of all of these is going to be this carbon-chlorine bond here, choice B. All right, these comparisons are not always straightforward. One way that we will sometimes help you if it's not a straightforward comparison is we can give you electronegativity values. So to illustrate how this difference in electronegativity works, if we write the two electronegativities for the two elements, again, I don't want you to memorize all of these, but if we gave them to you, or just to illustrate this topic further, I'll show them here. These are the electronegativities for all of these elements. So chlorine has an electronegativity of 3.0, carbon is 2.4, so that means the difference is 0.6. Whereas this one, chlorine is still the same electronegativity, 3.0. Silicon has a 1.8 electronegativity, so the difference is 1.2. So again, larger difference in electronegativity means more polar. So this is the least polar of those two, carbon and chlorine. So that's really what you're looking for here. It's not the individual electronegativities that matter. It's how different they are from each other, how far apart they are from each other. And that can often be rationalized just by how far apart they are left to right on the periodic table. So if you have, this comparison was not the easiest because it's dealing all with nonmetals and they're all kind of close together on the periodic table. But if you have a comparison between, let's say, a metal and a nonmetal, that's a really polar bond because those two are really far apart on the periodic table left to right, versus two nonmetals, which is relatively less polar. So some of those are going to be a little bit easier for you to rank and compare. All right, questions on this topic? Yeah.
So the more far apart they are, that's an increase in the polar.
Yes. So the farther apart they are, the more polar the bond would be. So the most polar bond in the periodic table is going to be francium, which is all the way in the bottom left, with fluorine, which is all the way in the top right. The noble gases don't really have electronegativity values because they don't tend to form bonds with anything. Remember that electronegativity is a property of an atom that's bonded to another atom, not by itself. And so francium and fluorine would give a really polar bond. We would conventionally classify that as ionic because the electronegativities are so different. But then if you go to an oxygen fluorine bond, those two are right next to each other, so that bond would be still polar but a lot less polar because they're closer together in electronegativity scale. All right, any other clarifications? All right, keep plugging on. All right, now we're talking about compounds and formulas. We want to know the formula of the compound that forms when calcium and chlorine react. So again, we need to know the atomic symbols, which from the answer choices are pretty obvious. So calcium and chlorine are the two elements. Now the first thing we should think about is what kind of compound will these form? So calcium being over here on the left side, chlorine being on the right. So what type of compound is this? Covalent or ionic? Those are only two choices. You have a 50% chance, and I won't judge you if you get it wrong. I promise. All right, I heard a mixture of each, but I did hear someone say ionic, so that is correct. Remember that there's only two types of compounds we've talked about so far. If it's a metal and a nonmetal in combination, that's ionic. One metal, one nonmetal, or sometimes a polyatomic anion is part of that. If it's two or more nonmetals, that would be covalent. So in this case, we have calcium and chlorine, which is a metal and a nonmetal, so this is clearly going to be an ionic compound. Not terribly important for this question, but it is helpful to think about because then we want to orient ourselves and think that we're going to form ions from these elements, and those ions are going to combine to make an ionic compound. So what kind of ion does calcium like to form? We talked about this concept earlier. It's 2+ because it's in the second column of the periodic table. It can lose 2 electrons to get to a noble gas. So we're going to have a calcium 2+ cation when these combine. And then what about chlorine? What does that form? Cations or anions? Anions and what charge? -1. So that's what this is asking. We have calcium in group 2A. All of those group 2A elements form +2 cations. Chlorine is in group 7A, the halogen group, and all of those form -1 anions. So then to find the formula, we just have to balance the charges of the ions. Calcium 2+, Cl-. Again, the dummy way of doing this is just to take the charges and make them the subscripts on the other element, and that gives us calcium chloride CaCl2. All right? Or alternatively, if you have a 2+ cation, you need 2 -1 anions to make sure the charges completely balance each other. All right, so the only answer choice that works is A. So predicting formulas of ionic compounds, this is a binary ionic compound, one where both ions are just single atom ions, not polyatomics. And for both those and ones that involve polyatomic ions, we should be able to predict ionic formulas and name them as we'll do in the next problem. All right, questions on this one? All right, we get a little bit more practice with ionic compounds on this question here, which wants to know which of the following name formula pairs is incorrect. So we give you the name and we give you the formula, and we have to see which one of those don't match up properly. All right, so in the first one here we have strontium carbonate, SrCO3. So we again have to think about the charges of the ions to make sure they're in the right ratio and the names that are correct. So Sr is strontium, and if we find that on the periodic table, that's here. So again, what charge would it be? Same column as calcium, so it's a 2+ charge. And then we have carbonate, which is CO3, and what's the charge on carbonate? Hopefully we're starting to learn these. It is negative, and is it -1 or 2 or 3? It's -2. Okay, so remember, learn your polyatomic anions is going to be a big help in all of your chemistry life, not just in this test. So, make an investment in your future and learn these. All right, so you have strontium 2+, CO3 2-. So that's the correct formula because they're equal and opposite in charge. So you need one of each to make a neutral ionic compound. But the problem with this is that the name here has this Roman numeral 2. And when do we use Roman numerals in the name? Or transition metals. So strontium is a main group metal. It's in these first two columns of the periodic table. So we don't use Roman numerals to indicate charges for group 1 and group 2. We only use Roman numerals for these transition elements here, and maybe a couple in the P block that we're not going to worry about too much. But the only time you have Roman numerals in the formula is this middle block of the periodic table, which is not where strontium is. All right, so there should not be any Roman numerals in the formula, so this looks like it's not the correct name if we're being really nitpicky about this. Now, admittedly, this is nitpicky because it's not necessarily wrong. It's the correct charge, and it doesn't, does identify this compound accurately, but it's just not the conventional way of naming it. We don't include Roman numerals. So that name looks like it's not correct. So we'll probably count that as our answer. Let's verify the other ones, make sure they are correct. So we have cobalt 2 nitride, CO3N2. Cobalt, in contrast, is a transition metal, so we do need to indicate the charge of the ion in parentheses when we name it. So that should have a correct charge. Let's make sure it's the right one, though. So for the transition metal compounds, we have 3 cobalts and we have 2 nitrogens. So what's the charge on nitrogen when it forms an anion? -3. It's in the group 5 column, so it gains 3 electrons. It forms an anion. So that means nitrogen should be 3-. The anion charges are invariant when you talk about those simple monatomic anions. So if we have 2 3- anions, what's the charge on the metal then? +2 to balance the charge. 3 + 2s, 2 - 3s cancel out. And so that is the correct formula and the correct name. Cobalt with a 2+ charge, the right ratio to balance that charge, everything matches up. For this one, we have calcium phosphate. As we've already talked about, calcium forms 2+ cations. What is the charge for phosphate? It's 3-. Okay, one of the other ones you'll have to learn. And so if we want to combine these two to form an ionic compound, we again take the charge and make it the subscript. So the correct formula for this would be 3 calciums and 2 phosphates. That's the formula we're given. That's the correct name, calcium phosphate, so that one's okay. Put check marks next to these to indicate that they're correct. All right, zinc sulfide, ZNS. This is another one that I gave you where I don't think we're going to give you any nitpicky questions about this, but just to make sure we're aware of it. So zinc is here in the periodic table. It is technically a transition element, which means it most often would have a Roman numeral next to it. However, zinc only forms 2+ cations. There is a table in your book that lists all the common cations, and this one would be in there. Again, I don't think it's necessarily going to come up on the exam, but just to complete the story, even though zinc is a transition metal, it only forms one type of cation, so it's still not necessary to indicate Roman numerals. The Roman numerals that you put for the charge are when that compound, that metal specifically, can have more than one possible charge. Zinc only has +2 charges, so we don't need a Roman numeral there. So ZNS is the correct name because zinc only forms a 2+ cation. Sulfur is in group 6, so it only forms 2- anions, and then those would combine in a 1-to-1 ratio to make zinc sulfide. And you don't need the Roman numeral here, again, because zinc 2 is always going to be a +2 cation. All right. Finally, last one, potassium chlorite. All right, we saw potassium earlier is +1. It's here in the first column. And then we have all of these oxo anions involving chlorine at the center. There's 4 of them, as we'll get into. So we have ClO2 is chlorite. That's the right name. And it's a -1 charge. So that's the correct formula, 1 of each. All right. Some of the hardest anions to remember are this series here. We have all these oxo anions with chlorine, ClO-, ClO2-, ClO3-, ClO4-. So remember that we start with hypo, that means low number of oxygens. The one that has the least number of oxygens is a hypo prefix and an ite and ending. Remember, ite means less oxygens. This one we remove the prefix and just call it chlorite. The ones that have more oxygen, 3 and 4, have an ate ending, so the first one is chlorate. And the last one we put a per to indicate that it has even more oxygen, so we put that as a prefix and still chlorate. All right, so these are probably some of the hardest ones to remember. Also keep in mind that we have these same types of anions that are possible for other halogens. So if you had bromine instead of chlorine, you would have hypobromite and bromite and bromate and perbromate. We could have hypoiodite, iodate, periodate. So the naming is systematic for these. So there's 4 of them you have to know, but if you know these 4 and the system behind it, then you can substitute any halogen in there, except fluorine, which never serves as their central atom. But chlorine, bromine, iodine all have these same types of anions. All right, so this is the correct name, potassium chlorite. So again, the only one that has anything wrong with it is choice A. Questions on nomenclature? Yeah. Why what? Why B is correct. Okay, so you can start with either, I guess, the name or the formula. We just have to make sure that they correlate with each other. So I think it's better to just start with the formula, because from the formula we can get the charge of the ion. So if you start with the formula, CO3N2, remember that transition metals can have variable charges. So we have to figure out what that is. So the nitrogen is always going to have a 3- charge as an anion. We have 2 of them, so that's a total of 6 negative charges. That means we need 6 positive charges to balance it. So if we have 3 metals, each of them must have a 2+ charge. So the correct charge is 2. This is a transition metal, so that should go in parentheses as a Roman numeral. And so cobalt-2 nitride being the name of the nitrogen anion when it forms a 3- charge is nitride, IDE, at the end. Okay? Yep. Zinc doesn't have a Roman numeral because +2 is the only cation that zinc forms. So I wouldn't say it's wrong to indicate it. So you could have it there, and I wouldn't necessarily, we're not going to be that nitpicky and say, oh, that's wrong to have it. But it doesn't have to have the 2 in parentheses, because it will only be +2. It will never be anything else as a cation. And that's because if we didn't talk too much about transition metal electron configurations, especially for cations, but the configuration for zinc is 4s2 3d10, and having a filled 3d10 subshell is a nice situation to be in. So it doesn't want to lose any of its d electrons. It'll just lose these 2 s electrons to form a +2 cation, but it's not going to lose any more d electrons because it wants to keep that filled 3d subshell. That's, again, beyond the scope of what we talked about, but that's why it only forms a 2+ cation. All right, other questions? All right, just a few more now. Now we're getting into Lewis structures. There's going to be likely, I would say, probably 2 or so questions on Lewis structures. The breakdown can be slightly different for different people. For carbon monoxide, so again, here we have to take the name and get the formula first. And then once we have that, we have to draw the Lewis structure and indicate the formal charge on the oxygen atom. All right, so what's the formula for carbon monoxide? Name the formula. CO, 1 of each. So remember, if there's no prefix, this is a covalent compound now, 2 nonmetals, carbon and oxygen. So we use prefixes to indicate how many of them are in the formula. No prefix on the first element means there's 1, and then mono means 1 for the second element, so it's 1 of each CO. So now we have to draw the Lewis structure of this. So we count electrons first. And that we again have to go back to the periodic table to find out how many valence electrons each of those has. Carbon is group 4A, so it would contribute 4 valence electrons. Oxygen is group 6A, so it contributes 6 valence electrons, 4 and 6. All right, there's only 1 of each, so that we have 1 carbon that puts in 4 valence electrons, 1 oxygen that gives us 6, and so we have 10 valence electrons in this small molecule CO. So now we have to draw the Lewis structure. It's only two atoms to bond to each other, so we can still follow the general process that we did before. We draw a single bond between the 2. Now we don't have a real central atom because there's only 2 of them, so it's arbitrary what we call central atom in this case. And then we have to start filling octets. Now, it doesn't really matter which octet we complete first, carbon or oxygen. However, by convention, and what usually gets you to the correct structure faster is to complete the octet of the more electronegative atom first. You don't necessarily have to do it that way in this case. You'll get to the same result. But I think if you have any doubt about, where should I put the next electrons, do the more electronegative atom first. So which one of these is more electronegative, carbon or oxygen? We talked about that earlier. So you're going to complete the octet of oxygen first, so you give it 6 more electrons to complete its octet. Remember, we have 2 from the bond already. So 2, 4, 6, 8, how many are left? So that means we put 2 on the carbon. All right, now if you evaluate this structure quickly, we have a problem here, which is that we have an octet on oxygen, but how many valence electrons are currently around our carbon atom? Remember, we count bonding and non-bonding for free octet. There's only 4. We have 2 from the bond, 2 as lone pairs. All right, that's not a good situation for carbon. So remember that with the exception of boron and beryllium, every other 2p element in that second row of the periodic table wants to complete its octet and have exactly 8 electrons ideally, if possible. So this only has 4, so how do we get more valence electrons? So I heard double bond and triple bond, so double bond would be the first step, yes, so we take 2 of these electrons and make a double bond, and then that will give us 6, and then if we do it one more time, we get a triple bond, and that gives us 8. So remember, the first thing we always want to do is complete the octet. Before we worry about formal charges or anything else, complete the octets first. And so we have to draw 2 more bonds. We can't add just 2 bonds because we've already used all 10 of our electrons. So we take 2 electrons that we originally drew as lone pairs on oxygen and turn them into a new bond. And so what that gets us to then, as was correctly stated, is a CO triple bond. We still have 1 lone pair on each of them. So that lone pair from oxygen is still there. That lone pair from carbon, that's 10 electrons, both have an octet. That's the only way to do this and be able to complete the octet of both, okay? And that should be your number 1 priority, again, with the exception of the few elements, boron and beryllium, that don't complete octets. But in any other case, you want to try to complete the octet first, which is what we did. And so now we can evaluate formal charges and see what we have. So we're looking for the formal charge on oxygen in this case. All right, so let's see what that answer comes out to. So remember that for formal charge, we start with the number of valence electrons that the atom itself has, which is 6 for oxygen. We subtract from that the number of bonds. How many bonds does oxygen have? 3. Remember, we count these each as individual bonds. So 3 bonds for oxygen. And then how many non-bonding electrons, total lone pair electrons, does it have? 2. We count those individually. And so that leaves us 6 minus 3 minus 2 with a +1 formal charge. And if we did our structure and our formal charge is correct, that means what should carbon be? It should be -1 because they have to cancel each other out because this is a neutral molecule. They should add to be 0. Let's verify that that's true. So carbon is going to be 4 valence electrons as we started with. It also has 3 bonds. It also has 1 lone pair of electrons, which comes out 4 minus 3 minus 1 is also, 2. Jeez. 2, we count these individually, -1. Okay? So we get a +1 and a -1. I put this in here because this is a weird Lewis structure. Because, first of all, it's rare to have formal charges in neutral molecules to begin with. Usually you'd have no formal charges if you have no charge at all. It's also rare to have the positive formal charge on the more electronegative atom. As we said before, if you have a negative formal charge, typically it goes on the electronegative atoms. This kind of violates both of those, but it's the only way to get the complete octet. So as I said, the octet rule needs to be your priority. So even though there's some weird things that come out at the end, positive formal charge on oxygen, you have a lone pair on carbon, which is pretty rare, you have formal charges in a neutral molecule, all these things are kind of strange, but you have to follow the octet rule, and if you trust yourself to do that, then those things should not alarm you too much. So we have a +1 formal charge on the oxygen, which would be the answer we put here. All right, questions on this or drawing Lewis structures? I think we have at least one more on Lewis structures, but if we can clarify anything now, I'd be happy to do it. Yes? Yeah, so if you're talking about elements that are these 2 p elements here, except for boron, so carbon, nitrogen, oxygen, fluorine, those should always get exactly 8 electrons. There's very few exceptions to that. Try to get 8 electrons in those. For elements below that, if they're the central atom, they could have more than 8 electrons. Often we will specify whether they should or should not follow the octet rule. If we say that it obeys the octet rule, those would also have 8. If it is possible to expand the octet, though, for some of these as central atoms. The outer atoms in your structure, whatever those are, should also typically have 8 electrons around them, excepting hydrogen, which just has 2. Okay? So yeah, in general, you want to try to get 8 valence electrons around those p block elements. Okay? Any other? There's one other over here, I think. Did I clarify that, or is there another question? All right. All right. Next question. We're back to nomenclature, so a little bit out of order here. But we want to know the proper name of the compound with the formula HClO2. So what we should recognize is that a formula that starts with H and then has an anion after it is what kind of compound? Acid. We just learned about these in class just on Wednesday, I believe. Last thing we covered for this topic, for this exam. And so the name of the acid is going to be dictated by the name of the anion itself. So ClO2, and this one we have a hint that this is going to be a -1 anion because it's one hydrogen in the formula, but ClO2 minus is one of the polyatomic anions. We reviewed it earlier and we saw that it's called chlorite. So when naming acids, you do need to know the name of the anion before you can start. And then this is what's called an oxoacid. So this is an acid that has a polyatomic anion, one of these ones that has one or more oxygens in it. And so for these, if you have an ITE anion, as we said, that becomes an OUS ending for the acid. If you have an ATE anion, so these oxoanions either end in ITE or ATE, those are the only two endings they have. And for the ones that end in ATE, you turn that into an IC ending for the acid, IC. All right? And remember that these oxoacids do not use a prefix, so you don't have the prefix hydro unless you're talking about a binary acid, which is just one that would have a simple non-oxo anion like fluoride, chloride, and so on. Okay? So no prefix. So we can eliminate C because it has a prefix. These should be named as acids so they don't have the word hydrogen in the formula. And then we have either ic or us. This is an ITE anion, so it becomes chlorus acid. That's the wrong ending there. All right, so again, not a whole lot with acid nomenclature. It's not a big topic because there's only, a dozen or so common acids that you'll even encounter in this course, but possible that we would have you name one of these types of compounds as well. So we have ionic nomenclature, covalent nomenclature, and then a subclass of covalent compounds being acids that we treat a little bit different. Questions on this one? We don't use hydro because it's not a binary acid. So the hydro prefix is only for what are called binary acids, which would be something that's just H with one other element, like HX, HCl, HBr, and so on, or H2S. It's just ones that have a single monatomic anion would be the binary acids, and that's the only time we use hydro. All right, anything else? All right, two more. All right, this one is a lot of effort, but there will likely be a problem with this type on the test. We want to use bond strengths to estimate delta E in kilojoules. Enter your answer with one place, decimal place, and no units. So this is a type of problem where we have to account for the sum of the bond energies of the bonds that are broken on the reactant side, the sum of the bond energies of the products that are formed, and then the difference between those gives you the delta E for the reaction. So for this type of problem, though, the first thing we have to be able to do is draw correct Lewis structures, especially for the ones where it's not obvious what the bond order is. Because as you'll see in this problem, I gave you 3 different carbon-oxygen bond orders, single, double, triple. All of those bond orders have different bond energies because as you increase the bond order, you increase the bond energy. And so we need to know in these reactant here that has carbon and oxygen, and the product that has carbon and oxygen especially, is that going to be a single, double, or triple bond? So we have to be able to draw Lewis structures sometimes for these types of questions as well. Now I'm going to give you some shortcuts for doing this. So in COCl2, carbon is the central atom. It's the least electronegative. And so we're going to have a bond to oxygen and 2 bonds to chlorine. Now we could go through the whole process of drawing the Lewis structure like we did before, count the electrons, distribute them, count for octet rule, all that stuff. I'm going to cover at the very end of this one more shortcut that's helpful for you guys to know with Lewis structures, which is that in most cases when you have carbon in a Lewis structure, again, carbon monoxide being a weird exception that we already went over, but in most cases carbon wants to form 4 bonds and oxygen wants to form 2 bonds. We're going to get some other patterns here in a little bit. But with that in mind, carbon wanting to form 4 bonds, oxygen wanting to form 2, what do we have to do to this Lewis structure to satisfy that? We draw a double bond. So when we say that they want to have 4 bonds, that's some combination of double and single. So now our carbon has 4 bonds and our oxygen has 2. The oxygen would also have 2 lone pairs. The chlorines would also have their lone pairs, but for this problem we don't really care about lone pairs, we just want to know what bond orders are. So there's a shortcut that can allow us to quickly determine that that should be a double bond, because carbon wants to have 4 total bonds. If we just draw a single bond, that's only 3. If we draw a triple bond, that's too many. And so we satisfy ourselves with a double bond. And then finally we have H2O, which pretty clearly is just 2 single bonds, because that's all that hydrogen can form. And then again on the product side, we could go through the Lewis structure of CO2, but if we have carbon at the center with 2 oxygens, carbon wants 4 bonds, each oxygen wants 2, so how do we satisfy that? So we want 4 total bonds on carbon, 2 total bonds for each oxygen, double bond on each side, okay? So that gives us, again, 4 bonds for carbon, 2 bonds for oxygen, so we would predict also that these are both double bonds. Again, we could have gone through all the steps of drawing the Lewis structure, you would have gotten to this, but for some of these problems, if we had to go through and draw all the Lewis structures from, step 1 to the end, and then we had to go through and do all these calculations, that's a lot of time, and you don't have unlimited time on the test. So I'm going to teach you at the very end some shortcuts for Lewis structures that will be helpful in certain types of Lewis structures, not all of them, but in certain types. And then we have just 2 HCl's where, again, hydrogen can only form single bonds, so we don't have to worry about bond orders for that one. All right, so those are all the correct bonds and bond orders that we have, so we have to sum up everything. So we have, on the reactant side first, we have 1 carbon-oxygen double bond, which is in this reactant here, CO double bond. So we're going to use that bond energy, which is 745 kilojoules. We're going to add up all of the bonds, though. So then we have also 2 carbon-chlorine single bonds, CCl single bonds, 2 of them because there's 2 chlorines in that molecule. That bond energy is given as 339. We have to double it, though, because there's 2 of them. And then finally we have water. There's only 1 of them, 1 water molecule, but there's 2 OH bonds. Remember that we have to count individual bonds in this case, not just molecules. So there's 1 molecule of water, but it has 2 individual OH bonds. So we have 2 OH bonds. And that's this number here, 467. So that's 934 for 2 of them. So we add up all 3 of these numbers, 745, 678, and 934, and we find that the sum of the bond energies that are broken on the reactant side is 2357. Then we need to do the same thing for the product side, sum up all the bond energies for the products. So as we saw on the product side, we have carbon dioxide, which has now 2 carbon-oxygen double bonds. So we have to count the bonds individually, as I said. So 2 COs. And that's going to be that number here, 745. So we don't end up using either of the other 2 CO bond energies. In both cases, they're double bonds. And then we also have 2 HCl's. Each of those has 1 bond, so we have to double the HCl bond energy, which is 427, so 2 times 427 for the HCl bonds. And that's 854. And then when we add those together, we find that the sum of the bond energies that are that are formed on the product side, I should say, is 2344. So then when we calculate delta E, we take the sum of the bond energies for the reactants and we subtract the products. So that number for the reactants was 2357. The number for the products is 2334, also positive, but we subtract it. And that gives us a relatively small number, plus 13 kilojoules. If this is a numerical question, which we would specify then to enter with no units, so you would just enter the answer in Blackboard as the number 13. All right, so don't try to put don't try to put units on any numbers. If we want you to enter a number in, it's always going to be unitless. I don't mind going back and looking at your answer, and if you make a silly mistake like that, I would consider giving the points back. That's all it was. But There's 500 of you, so the more of you that follow directions, the better off we'll be. All right, questions on this one. Like I said, there's likely to be a problem of this type on the exam, calculating bond energy. You're using bond energies to calculate change in energy. There's not a whole lot of variations in these types of questions. We could have had you solve for one of the bond energies where we gave you delta E, so a little bit of algebra could be involved. But it's really just one equation, one approach. But you do have to have accurate Lewis structures if we don't give those to you, to make sure you know the correct bond orders at the very least. All right, questions? Yeah, over here. Yeah, Joanna. Yeah. How do I know that? Because I've been doing chemistry for 20 years of my life. No, that's a bad answer. It's because, as I'm going to go through one more extra slide at the end to kind of go through this a little bit. So, typically speaking, in most molecules, carbon wants to have a complete octet and 0 formal charge. And the way it does that is by forming 4 bonds. If you start putting lone pairs on carbon, you're going to have formal charges. It doesn't want to have less than 8 electrons, so it needs to have 4 total bonds to get its 8 electrons. And so that combination, 4 bonds, no lone pairs, gives you octet with 0 formal charges. So that's why that happens. But I'm going to go through some more of those patterns at the end that might come up on the exam as well. But that's definitely a good question that we'll get to later on also. Anything else? All right. All right, last actual question on the review, but as I said, I have one bonus for you, one bonus slide to clear up one other topic. This is the right one, right? Yeah, because I changed this last question. So in the Lewis structure of Cl2SeO that minimizes formal charges, how many double bonds are there and how many lone pairs are on the central atom respectively? All right, so we're going to draw the Lewis structure of this molecule. We're going to minimize formal charges. So as we said, there's some times when it is possible to exceed the octet rule, and in this case, selenium being our central atom, the least electronegative, it is in the 3rd row of the periodic table, or below that, I guess, 4th row. So we could expand the octet if we need to minimize formal charge. So a lot of times, as I said, we'll specify either obey the octet rule or minimize formal charge. That way you'll know what's the final structure you should consider. So we're going to still follow the same process, though, to draw the Lewis structure of this guy. So we have 2 chlorines in the formula. So chlorine is group 7, so that's going to be 7 valence electrons. Selenium and oxygen are in group 6, so they would each contribute 6 valence electrons. So that's going to be our valence electron counting that we have to start with. We can't really use any shortcuts here because it's not a organic compound with carbon at the center, so we have to go through the full process. So we have 7 electrons from chlorine. And then we have selenium, which contributes 6 valence electrons. Oxygen, which contributes 6. So we get 26 valence electrons. All right, so then the next step is to put our central atom with single bonds, 1 oxygen and 2 chlorines. I should also specify, I probably should have done it here. If there's any ambiguity about what the central atom is, we will tell you. So I don't think there's going to be any questions where you're going to be completely thrown off by not knowing what the central atom is. It's either obvious or we tell you. So this one maybe is not the most obvious. We could have given it to you that selenium is the central atom. But when in doubt, as I said, put the least electronegative atom in the center. We start with single bonds to all the outer atoms. We complete their octets. We count how many electrons we've used so far. So we have 8, 8, and 8. That's 24. We started with 26, so there's 2 more. And remember, any of those leftover electrons end up as lone pairs on the central atom. So if we stop at this point, we can evaluate the structure, and we can see that our outer atoms have exactly 8 electrons, and our central atom also has 8. 2, 4, 6 from the bonds, 2 more from the lone pair. So right now, everything is happy from the octet rule. So if this question instead said, draw the Lewis structure that obeys the octet rule, we would stop here and not do anything else. But however, we want to minimize formal charge. We have to see if there are any formal charges and whether it's possible to get rid of them. So if we calculate formal charges in this molecule for, let's start with the central atom selenium. So remember, for formal charges, we start with the group number, which is the number of valence electrons, 6. We subtract the number of bonds. So how many bonds does selenium have in this structure? 3. And then how many non-bonding electrons? 2. So 6 minus 3 minus 2 is plus 1. So we do have a formal charge. We'll have to see if it's possible to get rid of it. For chlorine, we have 2 of them. They're identical, so we just have to calculate the formal charge once. And so for chlorine, they have 7 valence electrons. In this case, 1 bond for each chlorine. and 6 non-bonding electrons. 7 minus 1 minus 6 is 0. That's a pattern we should start to recognize. Halogens with a single bond and 3 lone pairs give you 0 formal charge. Very common arrangement. And then finally, the oxygen, last one, 6 valence electrons for oxygen. It also has 1 bond and 6 non-bonding electrons. So that gives you a minus 1 charge. So this structure that we first drawn, which completely obeys the octet rule, does have plus 1 and minus 1 formal charge. Our goal here is to minimize formal charges in this structure, as the problem tells us to do. So how do we get rid of a plus 1 and a minus 1 formal charge? We draw a double bond. Now, do we take the lone pair off of oxygen or off of selenium? Oxygen. Remember, we take it from the one that's negative and give it to the one that's positive. So we take off a lone pair from oxygen, make it into a double bond, and if we trust that that works, which it does, that gets rid of our formal charges. So now when we calculate formal charge, if we're doing selenium, we now have 4 bonds to selenium. So 6 minus 4 minus 2 comes out to 0. And when we calculate oxygen now, it now has 2 bonds and only 4 lone pair electrons. 6 minus 2 minus 4 is also a 0. So with this structure here, where we draw an SEO double bond, it does exceed the octet on selenium. Selenium now has 2, 4, 6, 8, 10 electrons around it. So it does violate the octet rule, but this is what we'd have to do to minimize formal charges. So we're looking for how many double bonds. There's 1 double bond. And how many lone pairs in the central atom. There's also 1. So choice B would be correct. 1 double bond, 1 lone pair on the central atom. All right, questions on this one? All right, the last one that I want to cover, which you may have seen something like this on the homework, is completing Lewis structures for larger organic molecules. So the approach I just went through works great if you have a single central atom, a few things bonded to it, and you're going to have to do that approach for a lot of the Lewis structures. But we will also sometimes give you pictures like this. And this is going to come up both in this chapter, where we just ask about the Lewis structure, as well as in chapter 4 when we start talking about bonding and geometry and things of that sort. So you're going to have to be able to do this. So we'll give you these larger, complicated Lewis structures, which are organic molecules. And we want to know, we want to ask you to complete the Lewis structure and then ask you some question about it, like how many double bonds or how many non-bonding electrons, whatever the case is. But obviously the trick is being able to complete the Lewis structure first. And this is where some of those patterns are going to be helpful. We could count the total number of valence electrons. We have 5 carbons, we have 5 hydrogens, and oxygen and nitrogen. So sure, we could count valence electrons. We could verify that our final structure has that. We could do formal charges, octet rules, all that stuff. But there's a lot of atoms in here, so that's going to take a while. So let's learn some patterns that can help us, that are in 99% of the cases going to allow us to get these Lewis structures very quickly and efficiently. So these types of molecules, as I said, have primarily these following elements. So they have a lot of hydrogen in them, and then carbon, nitrogen, oxygen, and then sometimes they'll have halogens, fluorine, chlorine, again, typically as outer atoms, not as central atoms in these types of structures. So in these types of structures that have these elements, remember that with the exception of hydrogen, the goal is going to be to complete the octet rule. So for hydrogen, we just form 1 bond and we stop. That's always true. And typically in these skeleton structures, these partial Lewis structures that we give you, you already have your bond drawn to hydrogen, so you're done with hydrogen. But then for the rest of these, we want to complete the octet and we want to minimize formal charges, and there's different ways we do that for each of these elements. So they all want to have 8 total electrons around them, and so for carbon, the way we do that is we just draw 4 total bonds with no lone pairs at all on carbon for these types of structures. For nitrogen, we still want 8 total, but it's going to be 3 bonds and 1 lone pair, LP being lone pair. So that's the combination we want for nitrogen ideally. As we saw in that other problem as well, oxygen is going to be 2 of each, 2 bonds and 2 lone pairs. And finally we have fluorine and chlorine. If they show up in one of these structures, which in this one they don't, those are going to tend to have 1 bond and 3 lone pairs when they're not the central atom in some other type of Lewis structure, okay? If they're one of the outer atoms. So this is the pattern we want to try to follow to be able to complete the Lewis structure of this molecule. So we go one by one. If we look at this first carbon here, how many bonds does it have? 4, so we're done. We don't add anything else to this carbon. No lone pairs ever on carbon and no extra bonds. If you have a carbon with more than 8 electrons around that, we call that a Texas carbon. That's not good, even though we like Texas. So keep it to only 8 electrons around carbon, or any of these elements really should only have 8 electrons around them. All right, this carbon here has how many bonds? And what about the one next to it? So they want to have 4 bonds, so how do we fix that? We double bond between the two. Can't draw the double bond to this carbon because that would give it too many, so it has to be between the two that are deficient, that have only 3 bonds to start with. So now both of those carbons are happy. This carbon here has how many bonds? Now this one's a little bit trickier to figure out because we have a couple of options of where to put that other bond here. But we have to also think about the oxygen. This has how many bonds? And it wants how many? So how do we fix that? Double bond between these two will make both of those satisfy. We have now 4 bonds on this carbon, 2 singles and a double. Remember, we count bonds individually, so it's 1, 2, 3, 4. This oxygen now has 2 bonds. It also wants to have 2 lone pairs, so don't forget about lone pairs in these types of structures. We might ask you about how many of those there are as well. So that finishes up the oxygen. And then finally, this last carbon here, how many bonds does it currently have? It wants 4. How many bonds does this nitrogen want to have? So how do we deal with that? 2 more bonds between those two will give this carbon a total of 4, this nitrogen a total of 3. Nitrogen will also have 1 lone pair. All right, so that's how we do these types of structures. Follow this pattern here, and you'll be able to quickly complete these structures. On this test, if you get this type of question, we're just going to ask something like how many multiple bonds or how many lone pairs or whatever are there. That's all we're, just Lewis structure at this point. But as I said, chapter 4 of these are going to come back in other contexts when we talk about bonding. All right, any last questions before I wrap this up? Yeah. Is there a pattern? Well, the pattern is 4, 3, 2, 1. Right? So that's how many bonds they get, and then the rest of the lone pair. Now, this only works for these types of organic molecules, so it's a little bit limited, but you'll want to use it here. Any other questions? Yes? How do I know when a bond gets weaker or stronger? So there's 2 factors that affect bond strength. So one of them is bond order. As you increase the bond order, as you go from single to double to triple, the bond will get stronger for that if it's the same 2 elements bonded to each other. So we saw that in this problem here. We had CO single, double, triple, and the bond energies increase as we go. And then the other factor that influences it is the length of the bond, whether it's shorter or longer. The shorter the bond, the stronger the bond. So those two are inversely related. Bond length is related to the size of the atom. So if it's 2 small atoms, they're going to form a short bond, and you expect that to be a relatively strong bond. If it's 2 large atoms, they're going to be farther apart, and they're going to have a long bond and be a relatively weak bond. So those are the 2 factors to consider, bond order and then bond length, which is related to the size of the atoms. Okay? Any last things? Yes? All right, so will there be a case where the pattern won't work? The only one I can think of where the pattern doesn't work, except small molecules like carbon monoxide that we already saw, or cyanide, which has the same number of electrons, Cn minus. But for these types of organic structures, the only time it won't work is if we have an NO2 group. So there's this group called nitro. So if you had this is called nitromethane. We don't have to know the name of it. But if you had this structure here and we wanted to complete it, there's no way to do it and follow all of these rules. Because if we give each oxygen 2 bonds, we're going to have now 5 bonds on nitrogen. So the way you would do this one is like this. You would draw 1 double bond, leave the other one as a single bond. In reality, these 2 are in resonance. The double bond moves between the 2. But you can't go any more than this because you can't exceed the octet of nitrogen. So it can only get these 4 bonds, and it can't go beyond that because it's in the second row. And you can't put 2 bonds on both oxygens for that reason, and there's no lone pairs in this case. So that's a little bit of a weird one that you might see, NO2, but other than that, they should follow all these rules. Yep. So the difference... Yes, so we're talking about the difference in electron activity for carbon, chlorine, and carbon, fluorine, which we covered here. So both chlorine and fluorine are more electronegative than carbon, but fluorine is more electronegative than chlorine. So yeah, as you go up the periodic table, the electronegativity increases, and so the difference between those two would be larger because it's well, you have to consider both atom elements together, but because carbon is shared between them, as you go up, yes, it would be an increase. It would increase the difference in electronegativity as you go up. Yes. All right, I think I'm going to stop the video here because if people have any last questions, feel free to come up and talk to me.